Next part in this chapter, that's about plane. So if you recall from geometry, we know that three different distinct points determines a unique plane. You know this determines unique plane, that is exactly one plane. So if you have three different points, suppose one point here, the other point here, and third point over here, these are the three distinct, I would say, known collinear points, then you will get the unique plane through these 3 points. So like this is a plane that passes through these 3 different points. Fine. So we want to get as a first theory as the equation of such a plane in a vector form. So here the first point, that's the equation of the plane through 3 distinct known collinear points. Points should be known collinear, remember. So let's write that. The first one, that's the equation of a plane. Equation of a plane passing through 3 points which are known collinear. Obviously, passing through points which are known collinear. Points are not collinear, known collinear. As I've shown here, they are not on the same line. Okay, so let's take those points as 3 vectors, because here we are doing in R3. So one is vector A, the other one is vector B, and the third one is vector C. So we have these 3 vectors here. Let me call this as vector A here, vector B here, and let's say vector C here. These are the 3 different known collinear points. So we have a plane through this. We want the equation of this plane here. Now you need to take one variable point here. Let's take for example P of vector R. Fine, this is one variable vector here. So if I join one vector AP here, one with this vector AP here, then one more I'll join here vector AB, one more I'll join here vector AC. So I form 3 vectors. Fine. Now I'll get the cross product of these 2. Cross product of which 2? AB and AC. So these 2 vectors are plane vectors. AB and AC are plane vectors. These are in the same plane. But if I take the cross product, you will get one vector like this, right? Which is nothing but what? Vector perpendicular to both of this, like this. This vector will be perpendicular to both of this. In fact, it will be perpendicular to every vector of the plane here. You know from previous chapter, cross product of any 2 vectors gives us the vector perpendicular to both. So here you can say vector AB cross vector AC is perpendicular to which vector? AP. Cross product of 2 vectors is perpendicular to every vector in that plane. So if I take the cross product of these 2, you will get one vector which is perpendicular to every vector of the plane here. So this will be perpendicular to this vector. If this is perpendicular to this, then the dot product must be 0. So AP dot AB cross AC, this dot product will be 0 here. Now if I write in terms of the position vector, you know this is vector R minus vector A dot, here inside the bracket. What about this? Vector B minus vector A cross, here vector C minus vector A. This is any variable point whose components are x, y, z, remember. This is a fixed vector, this is a fixed vector, equals to this 0. So this is known as the equation of the plane, remember. This is called equation of the plane. Equation of the plane. We need to remember this. Vector r minus vector a dot, this is one new vector. How we have got this vector? Just by taking the cross product of these two, as I explained, AB and AC. So this vector will be perpendicular to every vector of the plane. And once it is a perpendicular to every vector of the plane, it must be perpendicular to AP also. And therefore, the dot product of the AP and AB cross AC will be 0. And that's what we have used here. So this represents the vector of the plane through three distinct known collinear points. These 3 points are not collinear. They are not on the same line. So what's the equation of the plane? It is in the vector form. Vector r minus vector a dot vector b minus vector a cross vector c minus vector a. This represents the equation of the plane that passes through three distinct known collinear points. Fine. If you want to write in form of Cartesian coordinates, we can express in terms of the Cartesian coordinates also. So here, let me take this points as, let's take vector a as, for example, I'm taking x1, y1, z1. Vector b as, let's write x2, y2, z2. And vector c as, let's write x3, y3, z3. What I did, just have written in form of components because we want to write the Cartesian form. So, and this in fact you know, and vector r you know very well, that is variable point x, y, z. If it is r2, we take normal x and y, here x, y, z. Now if I use this, so use this vector r minus vector a dot vector b minus vector a cross vector c minus vector a. This is indirectly being cross product. This represents a determinant where first row is r minus a. So I'm just writing in form of determinant. What's the first row? R minus a. R minus a means this minus this. So you can write x minus x1. I'm writing r minus a, remember, y minus y1, z minus z1. What about the second row? That is b minus a. That is nothing but what? x2 minus x1, y2 minus y1, and z2 minus z1. And what's the third row? C minus a. That is x3 minus x1, y3 minus y1, and z3 minus z1. This is nothing but the Cartesian form of the equation of the plane. This is nothing but the Cartesian form of the equation of the plane. If you just simplify, this is a number, remember. X, Y, Z is the only variable. This is a number, this is a number, this is a number, and so on. So if you simplify this, we'll get such form: ax plus by plus cz plus some constant d equals to 0. Right? It would be indirectly in this form if you just simplify the determinant. It's just extension of equation of the line. If I drop this, it is similar to what? Ax plus by plus c equals to 0, remember. So it's just same as the equation of the line, but here third variable is added, which is z. Which form? This is nothing but the Cartesian form of the equation of the plane, remember. This represents the plane here. Ax plus by plus cz plus d equals to 0. Sometimes we can write like these also. Ax plus by plus cz equals to d also, remember. You take d on the other side, it will be minus d, and you can call that as d dash. Like these also. Both are the standard commonly used forms in form of Cartesian coordinates, remember. This is a vector form, as I mentioned earlier. This is nothing but which form? Cartesian form. Ax plus by plus cz plus d equals to 0. Now here in this form, you know that this is one vector which is perpendicular to every vector of the plane. So sometimes this is called the normal. So normal to the plane. Normal to the plane. What's a normal to the plane? That is a vector which is perpendicular to every point of the plane. Normal is a vector perpendicular to every point of the plane. That is defined as a normal here. A vector that is perpendicular to every vector of the plane. Suppose here, if I have plane like this, then you can consider one vector like this. This is known as a normal. Vector n, which is perpendicular to every vector of the plane. This is defined as a normal to the plane. Normal is a vector which is perpendicular to every vector of the plane. For example, if you consider xy plane, then z-axis will be the normal. In xy plane, z-axis is always perpendicular to xy plane. So that way here, one vector which is normally denoted by vector n, that is perpendicular to every vector of the plane. So now next form I want to write, that's the equation of the plane. So let me write that. That's very important form here. Equation of a plane. Equation of a plane through this fixed point vector A and with normal. So now you are given normal, remember, with normal as this vector n. In the first form you were having what? 3 distinct known collinear points. Instead of that, now what is given to you? One fixed point and normal you are given. So we want to write this. If you remember, in the previous case, in case of line, you used to take the direction and fixed point. Here we have fixed point and a normal to the plane. So suppose this is a plane here. One fixed point inside the plane you are given, that is vector A. And this is one vector which is perpendicular to the plane here, that is vector n, which is normal. That's perpendicular to normal, perpendicular to every point of the plane. Fine. Now you need to take one arbitrary vector here, which is vector r. So this is vector AP. This vector is inside the plane. Normal is always perpendicular to every point of the plane. So you can say, obviously, this vector AP, it's one point inside the plane, one vector inside the plane, is perpendicular to the normal. Perpendicular to the normal vector n. So therefore this dot product must be 0. Fine. Now here, what is the position vector of this? That is vector A r minus vector A dot normal equals to 0. So this is also standard vector form. Here, what is this vector n? That is just a normal to the plane. This is a fixed point through which the plane passes through, and this is just, variable point. Sometimes this you can rewrite like this, or you just open the bracket. So vector r dot vector n equals to vector A dot vector n, which is some, this is a fixed vector, this is also fixed vector. So dot product of two vectors is a scalar, so we write small d. Where what is d? Where d is nothing but, where d is given by vector A dot vector n. So this is also commonly used form. Here that fixed point is not known to us. Through which point this plane passes through, that we cannot determine from this. But if from this form you can find that vector r minus vector A dot normal equals to 0 here. Dot product of these two equals to 0, remember. This is the equation of the plane that passes through this fixed vector A and having the normal. The previous form, that was this form, that was about plane that passes through these three vectors A, B and C. So you can see that you just imagine this look like a normal only. R minus A dot normal equals to 0. Okay, so you can use this one as well as this one. This is a vector form of the plane, remember, vector form of the plane, which has vector n as a normal and passes through this. And the Cartesian form, if you rewrite, as I told you, Cartesian form, here let vector r as x, y, z, variable point always, and normal I'll take as, for example, a, b, c. These are the components of the normal. Now use the dot product here. So if I use the dot product, so using this, you'll get this equation, dot product of these two. So you'll get the ax plus by plus cz equals to d, or you can write plus d equals to 0. That's not important because d is a scalar. So this is the Cartesian form of the plane, right? Again, I already told you, this is I'm saying that this is just similar to which form? Equation of the line, if you remember, Cartesian equation of the line. What was the Cartesian equation of the line, if you remember? It was this ax plus by plus c equals to 0. This is nothing but what? Line, equation of a line in R2. Here, this represents the plane in space, remember, ax plus by plus cz. You can write plus d equals to 0, or you can write equals to d, both are same. What is this? A, B, C, these are nothing but what? Direction ratios to the normal to the plane, remember. Here, if you remember, you can find slope very easily by minus a by b, if you remember. From this, slope can be obtained very easily using the concept of minus a by b, just recall. So from the line you can get the slope. From the equation of the plane you can get the components of the normal, that is the direction of the normal to the plane. That is also called what? Direction ratios. That is nothing but the coefficients of what? X, Y, Z. What are the coefficients of X, Y, Z? A, B, C. That is nothing but the normal to the plane. So this very important form we'll use frequently. This one as well as this one, remember. So now onwards, whenever you want to get the equation of the plane, we always ask two things to ourselves. Number one, point and normal. The first one, that's a fixed point, and the second one, that is a normal. In line in R3, you were asking for what? Direction of the line and fixed point. Here now next form, that is equation of a plane. Equation of a plane on which a perpendicular from origin of length, say small p, is drawn. Is this, we want to write this. What we want to write? Equation of a plane on which a perpendicular from origin of the length p is drawn. Okay, so I'll consider three coordinate axes here. You will realize once I draw the diagram what's the question. So let's see this three coordinate axes. So we have here x-axis, this is y-axis, and this is z-axis. This is origin. The required plane is this. We want the equation of this plane, remember. This is the required plane. We want equation of this plane on which we have drawn one perpendicular. This is a perpendicular to the plane. Say ON, this is vector ON, and the length of ON equals to, as you are given, it's a small p. Okay, so vector ON is perpendicular to the plane, and What's the length of the perpendicular? That's small p. So ON equals to small p here. Okay, this is your given. Now we want the equation of such a plane. Fine, that's a question. So what we do, we consider a unit vector in the direction of this. So let's take, I'll write n cap be the unit vector in the direction of vector ON. So therefore you can say that n cap is nothing but the vector ON upon its length. But what is the length of this? Your length of this one, you know, it is small p. So therefore you can say that the vector ON is nothing but the p n cap. Vector n is given by this. N cap is unit vector, remember. Okay, now we want to write the equation of the plane. So how do we write that? You know, you have normal here. The n cap itself represents a normal. So you have normal as well as one fixed point. Which fixed point? That is this vector ON. That's inside this n. So here equation of the plane is this. I'm not showing that theory portion. I'm writing directly here. Vector r, you know, it is always there. Dot here n cap equals to small p, remember. Right? If you use this concept, you will get this. Don't get confused with this n cap, and we had earlier one of the form with that. That was which form? It was here r dot vector n equals to d. Here n is any vector. This is a unit vector, remember, in the direction of the normal. Here d is any scalar, remember, that is obtained through this. But what is p here? P is this perpendicular distance, as I told you, right? This can be derived. I'm not showing that. I have written this directly, but this is a required form. This is a plane on which a perpendicular of the length p from origin is drawn. What is that form? Vector r dot n cap equals to small p. What is small p? Small p is nothing but the perpendicular distance from the origin to the plane. This is the distance from origin. Distance from origin. That's one thing. What is this? This is unit vector, remember, in the direction of the given normal, remember, that's a perpendicular to this. This is a unit vector, and this is, you know, variable point, that is nothing but x, y, z normally. So let me take one simple example. You will realize here I'm just taking one example. So for example, you are given the perpendicular distance p equals to 6 by root 29. This is given to you. Find the plane that is at a distance of 6 upon root 29 from the origin, and its normal vector from origin, that's also given to you, from origin, that is equals to 2i cap minus 3j cap plus 4k cap. That's given to us. What's the question? We find the equation of the plane. That's the question. We find equation of the plane. Equation of the plane. Okay. Two things you are given. Perpendicular distance from origin to the plane, that's a small p as per our notation, 6 by root 29. Normal vector from origin to the plane, that is this much. Now recall the theory. What's the equation of the plane? The equation of the plane, you know, it is given by here. The equation of the plane in the vector form, if you recall, equation of the plane, that is vector r dot n cap equals to small p. Now this should be unit. Here you are given just normal vector, so you need to make this unit, so you'll get the n cap. So here what is n cap? That is nothing but the 2i cap minus 3j cap plus 4k cap upon its magnitude. What is its magnitude? 4 plus 9 plus 16. So this become root 29. So root 29 upon you have 2i minus 3j plus 4k. Right? So this is normal. Now we just place here. So therefore plane is here. Equation of the plane is r dot, you are just going to put this. So what will get? 2 by root 29 I cap minus 3 by root 29 j cap plus 4 by root 29 k cap equals to, what will get? P, small p. Small p is how much? 6 by root 29. So if you want, you can simplify this. So you can take vector r as x, y, z and you can just cancel with this. So we'll get here, if you want to write one more step here, take root 29 outside, it will get cancelled with this. 2i cap minus 3j cap plus 4k cap equals to 6. That's a vector form. Fine. And you can get the Cartesian form also just by placing what? R equals to x, y, z. This is a vector form. Vector form of the plane on which a perpendicular of the length p6 by root 29 is drawn from the origin. This is just a normal vector. So what we did extra here, you just convert into unit vector. So we have these and therefore we have this. Fine. The next form, that is equation of a plane making intercepts with the axis, making intercepts with 3 coordinate axis. We had the same form in case of the straight line also. So let me show you what the question says. I'll consider 3 coordinate axes here. These are the 3 coordinate axes. Here we have x-axis, this is y-axis and this is z-axis. Okay. This origin, we have a plane like this. Let's consider a plane. So that intersect x-axis as one point A with 3 coordinates a, 0, 0. So this become x-intercept. With y-axis it intersects, suppose at B, so 0, B, 0. So this become y-intercept. And with z-axis, let's write here 0, 0, C. So this become which intercept? Z-intercept. So A, B and C. A, B and C, these are the 3 intercepts. Indirectly you can say that the plane passes through which 3 points? A, 0, 0, 0, B, 0, 0, 0, C. So here intercepts are this. What are the intercepts here? A, B and C with 3 axes, remember. With axis. With axis means what? This one with x-axis, this is with y-axis and this is with z-axis. So the equation of the plane in this case, equation of the plane is, as we have discussed, x upon A plus y upon B plus z upon C equals to 1. This is the required plane which has small a intercept with the x-axis, small b intercept with the y-axis and small c intercept with the z-axis. How will get this equation? Very simple. Use the first theory. Equation of the plane through 3 distinct known collinear points A, 0, 0, 0, B, 0 and 0, 0, C. You will get this. This much you can do. But we had a similar form in straight line. If you remember, line with 2 intercepts, it was, if you recall, x upon a plus y upon b equals to 1. This is a line that has small a intercept with the x-axis and small b intercept with the y-axis. Similarly, here we have the equation of the plane which has a, b and c intercepts with the 3 coordinate planes. Okay, now next, that is let me write here equation of the plane, equation of a plane through the intersection of the given two planes, intersection of two given planes. We want to get the equation of a plane that passes through the intersection of the given two planes. So I'll consider two planes which are intersecting. So let me show you here. For example, this is one plane let us call pi 1. Suppose this is another plane, one more plane, let me call that as pi 2. So this is the intersection. So through intersection you can find number of planes. Remember, there are infinitely many planes through the intersection. So we want to write all such possible planes, plane pi for example. Right. This is a plane that passes through the intersection of the given two planes. Where this is one plane, this is another plane, this is the intersection of these two planes. Here this is, I've just shown one plane. You can find many such planes. You can draw one more over here also. So there are infinitely many planes through the intersection of these two planes. So this is similar to one of the theory which we did earlier in case of lines, if you remember. So here this is not just one plane, but it's a family of planes. So planes through intersection is here one plane plus some scalar. You can write lambda into the other plane equals to 0. That's the general theory. We had such theory in case of lines, if you remember. One plane pi 1 plus lambda into the other plane pi 2 equals to 0, where lambda is a scalar. Lambda is any scalar here, remember. If you choose different values of the lambda scalar, you will get the different planes through the intersection of the given two planes. So this, for different values of the lambda, you will have the different planes. So this is not just planes, this represents the family of planes. What's the theory here? One plane plus scalar into the other plane equals to 0. So whenever you have such question, plane through the intersection of the two planes, then always you use this. Which theory? One plane plus lambda into the other plane equals to 0. And then you will be having certain condition the question. You will get the lambda and again in turn you place it. We'll see once we do exercise questions. But this is a general concept. One plane, you write the first plane plus the scalar, the second plane here equals to 0. Right? That's a theory here. As I've shown here, this represent here plane through the intersection of these two planes. And as I told you, this is not just one plane. There are a number of planes through the intersection of these two. Okay. So now, next theory is distance of a point from a plane. Distance of a point from the plane. So let's write the equation of the plane by this. I'm using Cartesian form. Ax plus by plus cz. Here let's write plus d equals to 0. You can write equals to d also. And the point be this here. Point B, suppose P of x1 y1 z1. This is the point. So it's like this. Here there's a plane. This point P, we want this perpendicular distance. Let me call this as PM, for example. Perpendicular distance of a point from this foot, remember this one. This is called the distance, perpendicular distance. So it is also similar to one of the theory from the straight line. So that distance is given by here modulus of x, y, z is replaced by this x1, y1, z1. So x1 plus by1 plus cz1 plus d, this much, upon root of coefficient square, that is a square plus b square plus c square. That's the distance formula. This gives us distance of this point, which is not inside the plane obviously, from the plane, this much. What is that? It's very simple formula. If this is a fixed point that's given to you, and if this is the equation of the plane, then just x, y and z is replaced by this one, x1, y1, z1. So ax1 plus by1 plus cz1 plus d, this much only, upon root of not x1 square, y1 square plus z square, but a square plus b square plus c square. This gives us the distance of the point P from this plane. Same theory you had in case of the straight line. Take z equals to 0. So if you remember, you had such theory in case of the straight line in 11th standard. Ax1 plus by1 plus c upon root of a square plus b square. Now instead of any point x1, y1, z1, if I take this as origin, then this is just modulus d upon under root a square plus b square plus c square. So I'll write in particular distance from the origin, in particular if P is this 0, 0, 0, that's origin, O 0, 0, then the perpendicular distance, then the distance will be, you know that x1, y1, z1 becomes 0. This is 0, this is 0, this is 0. So it will be just modulus d upon we'll get the root of a square plus b square plus c square. This is special case of the above formula. This was for any point x1, y1, z1, remember. Here this is specially for origin, so this 3 will be 0. So your modulus d upon root of a square plus b square plus c square. Now next we want to write, that is perpendicular distance between two parallel planes. So let's write that. The distance between two parallel planes. So we take two planes here. Let's write like this: ax plus by plus cz plus, let's write here d equals to 0. And if two planes are parallel, then the coefficients are same, remember. So I need to take some another constant. Let me write d dash equals to 0. What's the normal to this plane? You know, ABC. And what's the normal to this plane? That's also ABC. Either they are equal or they are multiples. From the equation itself, you can say that the planes are parallel. These two planes are parallel, remember. They differ by constants only. One is d, the other one is d dash. Like this. Here we have one plane. And one more plane is over here. Such planes. This is the direction of the normal of the first plane. This is the direction of the normal to the second plane. So they are either equal or they are multiple. So that's why we have chosen in this way. You know, in case of the straight line also, whenever they are parallel, slopes are equal. So here normals are equal, or you can say they are in the same direction. That's why we have chosen in this way. Okay. So we want this distance, perpendicular distance between these two parallel planes. So here perpendicular distance, distance means always perpendicular distance between the planes, that is equals to difference of these two constant, that is d minus d dash with modulus upon root of coefficients of x, y and z, a square plus b square plus c square. This is the length of a normal indirectly. Right? Here they should be equal. If they are different, you need to make them equal, remember. So this formula, we had same formula in case of the straight line, if you remember, c minus c dash upon under root a square plus b square. This was the formula to get the perpendicular distance between two parallel lines, 11th standard. C minus c dash upon under root a square plus b square. Here only third component is added, that is c square. The perpendicular distance between the parallel planes, that is given by modulus of d minus d dash upon under root a square plus b square plus c square. Fine. Now one more thing we want to write here, that's angle between two planes. The next point is angle between two planes. So we take two planes here. One plane I'll write in the vector form, vector r dot, here normal n1 equals to constant d1. The other plane, this is a variable point, normal n2 equals to d2. So these are the two planes with the normals n1 and n2. I wrote in the normal form, vector form. Can express in Cartesian form also. So it's like this. I'll try to show this. Here we have one plane with normal, the other plane, let's see, like this. This is the other plane. This is their intersection. So here angle will be, you can take this as a theta. This will be obtuse angle. This is a normal to this plane. Here this is a normal to this second plane. N1 vector N2. Now here it's difficult to visualize, but angle between these two is same as the angle between their planes. So I'll write here angle between two planes if and only if angle between normals. Now normals are, vectors. So we just write angle between these two vectors. Which two vectors? Normals, that is n1 and n2. Let the theta be the measure of angle between these two planes. So therefore, which formula? The same which you had in case of the vectors. Cos theta equals to normal n1 into normal n2 upon their individual magnitude. Right? This just comes from the vector only, but here it is always taken as an acute angle, so we put modulus here. In case of vectors, you obtuse angle. This is just from the vector, as you know. We did the same formula for lines also. There it was cos theta equals to vector A dot vector B upon their magnitude, if you remember. This is for angle between two vectors, vector A and vector B. Here this gives the angle between two planes. Angle between two planes is same as angle between their normals, remember. So cos theta equals to normal n1 dot normal n2 upon their magnitude. And why we have placed the modulus? Because in this case the theta is always from 0 to pi by 2 to make it acute angle. Right? In case of the vector, it was obtuse angle, if you remember. If as a special case, if the dot product equals to 0, that means normals are perpendicular. In that case, the angle between two planes is 90 degree, which is pi by 2. If normals are parallel, if normals are parallel, that is multiple of one another, if and only if planes are parallel. So angle between two planes is 0. Normals are parallel means what? They are multiples, positive or negative. That means planes are parallel. And then theta is 0. If dot product is 0, that means two planes are perpendicular to each other. So theta is pi by 2 or 90 degree. Okay. Now the next and the last theory, that is angle between plane and line we want to write. So the next one, that is, let me write here, angle between a line and a plane. A line and plane. So let's see that. So we consider first equation of a line. You know, line is given by this one in a vector form, vector A plus lambda vector B. So what's the direction of the line? Vector B, where lambda, you know, it's a scalar. And plane is given by which form? In a vector form. If I write vector A dot normal equals to scalar D, where D is a scalar. Okay, so let's take this as a plane here. It has a normal and this is a line. Let's consider line like this that intersect this plane here. So we want this angle here. This angle, let's call that as theta. There is a line here. Okay, so I'll write here, let theta be the measure of angle between these two. Angle between these two, between line and plane. Okay. So let me show normal here. Suppose this is a plane. Let's take normal by this. Okay. This is perpendicular to the plane here, normal. This is the direction of the line here, which is vector B here. Now this is also theta. So if this is theta, you know this is 90. So in this triangle, this become, you know, 90 minus theta. Right, this angle. Now what is this? This is angle between here normal to the plane and the direction of the line, which is vector B. So if I use that formula, cos, now here angle is 90 minus theta, which is angle between normal and direction of the line upon their magnitude. With obviously this again acute angle, so we put the modulus. Now what is cos 90 minus theta? It is sin theta. So you have this much upon their magnitude. So this is the formula to get the angle between plane and line. Here left hand side you have sine function, remember. In earlier all formulas you had cosine function. The sine theta equals to dot product of the normal to the plane and the direction of the line with modulus upon their individual modulus. This right hand side expression is very common. If you are talking about two lines, then dot product of the directions with magnitude. If you are talking about two planes, then dot product of the normals upon their magnitude. Here dot product of the direction of the line and the normal to the plane. But here left hand side, instead of cos you have sine function. Why this is 90 minus theta? We have used the same formula from vectors only, cos theta equals to that expression. But here instead of the theta, the angle between these two vectors, which two vectors? That is this vector B, direction of the line, and normal to the plane is not theta. Theta is here, remember. This is theta, this is 90, so this has to be 90 minus theta. This is nothing but the 90 minus theta, remember, in this triangle. So cos 90 minus theta equals to dot product of normal and the direction of the line upon their individual modulus. So this is all in all about theory portion of the planes. In the next session we see the next exercise.